One of the more troublesome things about being human is that you don't get a whole lot of time in order to figure things out. We get like roughly 70, 80 years, maybe if we're lucky, or 90 years, and some people less. And so the story of humans trying to figure out time and our place in time has always been a difficult one. We've had history for about the last 6,000 years or so. But other than that, it's been kind of a crapshoot, and people make up things in order to take the test, I guess you could say. So we have some things that we know in geology, and so I guess what I'd like to say is, from this deeper understanding that folks have built upon over the last 200, 300, 400 years, we're going to build a mindset for you in order to turn you into a time traveler in some ways. And so as a time traveler, you're going to have some responsibilities. A lot of people don't understand the concepts of time all that well. So that's the topic for today. We have 3 different segments, 3 different modules, one module and 3 different deliveries to talk about time. And so let's just go ahead and begin. Thanks. Bye. So many of you recognize already that we have 3 dimensions that are easy to detect in this world. So that's the length and the depth and the height. And that's 3 dimensions right there. And then we also have time. Now, time is an unusual one because it doesn't have the same physical manifestation in space. Okay, so time, in fact, is more about change, how things in the 3 dimensions will change through time. And so if it is considered to be a 4th dimension, it and space together, actually those 4 dimensions kind of govern a few things about how we understand the universe. For instance, we know that gravity affects the space-time continuum. And we also know that, it affects the pattern of the pathway of light as well. That's how they can detect satellites around far distant stars, exoplanets, if you will. I hope I said that right. Planets around stars far, far away from the Earth and the sun and the solar system here. So we're talking 4,000 planets have been detected pretty much in that way by a deflection in the space-time continuum, by the gravity and how it affects the space-time continuum. So with that in mind, we're going to ask some questions here. So what is time is one of the questions that we have to ask. And then, can we go back in time? And how do we measure time? Does time actually slow down? Maybe you've been in a situation. I've been in a bicycle accident, for example, where it seemed like time slowed forever. And, it's like, no, anyway, we're going to talk about that. Does time actually dilate or slow down, get larger or smaller? And then what is relative age dating? There's going to be a separate presentation on that. And then also a separate presentation on what is absolute age dating. So those are the questions we ask when we come to the idea of time. Now, you've already been asked to learn the geologic timescale, and I've given you the GSA timescale to memorize. It's a practice one that you have to memorize for week 2 in here. So we live in these 3 dimensions. You can see here on the next slide, and it shows it's a Rubik's Cube, of course. We can't actually see time. We can see all of the other dimensions, but we can't see time. But time helps us to measure the sequence of events, okay, the motions of objects, and so that's one of the things that we deal with in geologic time, even, right? And so, but we can't go back in the past and see what was happening then, at least not yet, and I kind of doubt if we ever will. But at the same time, we can try to piece together what happened back in the geologic past. In the next slide, you can see the space-time continuum. This is artist's representation of what it's like to have gravity bend the space-time continuum. So it's oftentimes you'll see science experiments where they have like a funnel, and you can release a series of marbles and watch the marbles spin around the funnel until finally they are taken into the center of the funnel. But that's the idea about a space-time continuum. And you can go to Wikipedia and look up more of these things if you want to know more in detail about space-time, for instance. So can we go back in time? It's only been in the last year that somebody said, yeah, we can go back in time, but only for a very, very short duration. And then you spring right back to the time that you were in. Now, that's from like quantum physics, I think, that they've been able to show things that do that sort of behavior. But in general, can human beings go back in time? That's not going to happen likely in our, remember the three laws of Clark, right? And so not likely, at least not literally, we can't right now. So maybe someday, for these short durations, who knows? But if you did go back in time, here's the conundrum that would represent. Can you go back and kill your parents? If you did, you wouldn't exist, and so therefore you wouldn't have been able to have gone back in time. So those are the sort of things that, the paradoxes we call them, that exist if you could go back in time. So one of the other things to keep in, actually, there was an episode of Futurama that dealt with Fox, what's his name, Fry, being able to go back, and he became his own grandfather, I think it was. And so anyway, that's a nice little animated television show that showed a lot of interesting scientific ideas as well. So the next question is, how do we measure time? And that's changed through time considerably. And on this diagram, you can see, of course, the sundial. And that's the same thing that you saw on the first page of this presentation. It was a sundial that was mounted to a building from southeastern Germany. It was in Nordlingen, actually, the first sundial that you saw. Here's one that's just a standard, one that you can buy off of the internet here. A sundial with the marker on it there, and so the sun marches through the course of a day. Of course, it doesn't work very well at night. The next one is an hourglass, they call it, because you have to keep flipping it over from hour to hour, and the sand falls through the hourglass, so goes the days of our lives, or something to that effect. And then lastly, the third one here actually works. You can use it at night as well. And it's called Foucault's pendulum. And this is, I think that is in the British Museum. And so the pendulum actually marks the time of day because they get it moving. I think it's a 16 kilogram weight at the end of the pendulum, and it goes all the way to the ceiling, of course. And as the Earth spins, so too does the motion of the pendulum change across the face of it there. Now, I don't know how often they have to start the pendulum up again. I would assume that this thing would last for several months before you'd actually have to draw it back out to the edge in order to get it to swing again. It's nearly frictionless. You have the friction of the air, and that's about it that's on this pendulum, and that's what slows it down eventually. But that is a timepiece of sorts. Not something that's very convenient to use, however. In contrast to that, we have things like pocket watches. And so here you can see one of the more famous pocket watches is called the H4 chronometer. And it was a fellow named John Harrison who came up with this. And in addition to just time alone, time was very influential in early sea navigation as well. When Captain Cook was going to do his circumnavigations around the world, he took a chronometer, one of Harrison's chronometers. I don't recall if it was H4 or if it was H2, but one of these chronometers he took with him around this voyage around the globe, and it lost only a few seconds, I think, in the course of the entire voyage. So you can measure time very, very accurately with these sort of mechanisms. And so Harrison was competing for a prize to try to solve the riddle of longitude, because it's easy to tell where you are on the globe with latitude because we are at some elevation relative to a fixed canopy of stars, essentially, even though those stars will move through time. But from the North Star, you can actually sight the North Star. You can sight the Southern Cross in the Southern Hemisphere. and kind of tell where you are with latitude, but longitude was always the difficult one, and they had to do a lot of dead reckoning before the 1700s in order to figure out. They had to estimate how rapidly their ship was moving, and of course there's always ocean currents and things like that that you have to navigate with and try to. So they called it dead reckoning, in fact. That was one of the ways. And so they would also do things like drop a keg off the back, an empty keg, and then you would count how many knots out that keg would be floating before you'd pull it back in again. And so you can make estimates over the velocity of that ship on the sea. A few more examples on here. You can see the Felix the cat who wags his tail. And then also the time clock, very important. At least it was back in the day when I was doing hourly work. And so you had to punch the clock every day. With the quartz crystal there, it's a very interesting phenomenon. And you've probably heard of quartz clocks and quartz watches and so forth. And quartz has this unusual capacity. It has a property called piezoelectricity. If you strike quartz, it actually gives off a small pulse of electricity. And so that electrical sort of current helps to keep a clock regulated. And so the clock mechanism, which is very accurate just from a mechanical standpoint, with all of the gearing and then also a catchment that keeps the ticking part of a watch working, quartz made it possible to kind of streamline that sort of process with electric watches and so forth. So it was just a handful of different watches. In the next little video I'm going to show you here, this video, you can actually see me winding up my father's watch. Now this watch was built in 1947. It's a railroad watch, and my dad was a civil engineer, and he used to do surveying quite a lot, and so his important thing for him was to maybe do what he called star shots, and well, what surveyors call star shots. And so even in the middle of the day, you could take a sighting on the North Star in order to be able to determine exactly what your latitude was. And so he would use his theodolite or his instrument in order to be able to take star shots even in the middle of the day. And he had to know very precisely what the time was. And so that's what the railroad watch was very good for. And so I haven't kept, I keep this pocket watch wound most of the time. It's kind of a ritual for me, but it's one of these things that is, it's lost its accuracy over time, although it's consistently inaccurate. Let me put it that way. So it loses about a minute or two every day. But if I were to adjust it, you take the back off and make a few adjustments. And over the course of about a week or two, you can set that thing to where it's very precise again. And so I just haven't taken the time or the... So if we look for the most accurate clocks, that would be the cesium clock here. That's the one that they use at the Bureau of Standards in the United States. And this, I think it's in Boulder, Colorado, National Institute of Standards and Time. And so this is one of the clocks they have, in fact. So it's a NIST F1 cesium fountain atomic clock, and radioactive decay is not a pendulum, if you will, but it is more of a stochastic process. And so it tends to be with cesium, because the half-life is so short, it's easy to get that clock to very accurately keep time. And so even if we don't have a good understanding of what time really is, we know that we can still measure it even if we can't see it. And so we measure it, but that's kind of based off of human sort of observations, if you will. So it's the observations of how many atoms will change, or how many ticks of a clock is it, so those things are kind of arbitrary in some ways. And if you think about it, ever since like the caveman days, we've had a way to keep time. That's days. And then the seasons are another way, right? And so our seasons would change because the Earth is at an angle. It's tilted slightly. And so there are other things that we have too. We have the tides. We have, even the eclipses would be predictable even to early man, humans, to be able to detect what the time is. And so, but this is the most sophisticated version right here. And so it was Salvador Dali. who painted this in 1931, The Persistence of Memory. And you can see the clocks because memory is very good for impressing upon us, things that have happened. But here's, actually it's a self-portrait, Salvador Dali down here with a clock draped over him and a clock draped over everything else in here, and the ants slowly attacking another clock there and attacking, the even the ravages of weather and the seas have made cliffs and so forth in the far distance here. And so Salvador Dali, Catalonian, as I recall. And so here we have just a depiction of how warped time can be in our own frame of reference. For other ideas, does time slow down? Okay, so the general consensus is no, and that is time does slow down if you get closer and closer to the speed of light. So they tell us. That's the physicists who tell us that. But if you take a fixed, there's no place that's fixed, okay? But if you are on a frame of reference that seems to be not changing very rapidly, it may seem at times, like if you're having a bicycle accident, like I mentioned previously, you may have heightened perception of what the time is. And so there's a very interesting way that they tried to figure this problem out. They strapped a digital watch onto an observer's hand and his arm, and they pushed that person off of a platform about 80 feet up in the air. And that person would then fall to a net down below. I guess they tried it other ways maybe first. I don't know if they did that or not. But they would ask the person who was surprised, falling all of a sudden, whether they could actually see the digital watch, which was clicking off the numbers very, very rapidly, if they could actually see the numbers, because typically it's a faster rate than what the human eye and the brain can conceive of as you're falling. And so, in fact, the observers who were trying to look at their digital watches, they were surprised as they were falling backwards through space and landing in a net, like at a circus. This would be something that they might remember, but no, it turns out that there was just a blur anyway, whether you're looking at it standing still or falling. And so there's an interesting article about it. It's called the SCAD diving that they tried there. Now, with that in mind, keep in mind also that the observer has a very sophisticated device with which we try to measure time. That's our brains, right? And so what they find is the brain takes little mini vacations on a much more rapid scale than what you might think. Like up to 5 times per second, your brain kind of click out a little bit. And what they've done is they've tracked where your eyes will move, the direction of your eyes. And so sometimes you can see, and these things are called Circades. Circades are where you momentarily are distracted or you lose perception for just a brief instance and then are drawn right back into the narrative in which you were involved. And so you may notice this also from clocks that have sweep second hands, where if you look at the clock intently and you can see the clock going around, then all of a sudden it looks like it stopped for just like a brief, less than a second maybe even. That's what these Circades are. And so your eyes are actually drawn away. That affects people in a lot of different ways. So I assume that, like, for instance, race car drivers or Olympian shooters would have a better control over the Circades that they experience than other folks do, or they've learned to compensate for them in some way. So anyway, that's an introduction to what time is. There's some great songs about time. That's another nice thing that we have in this world. So the music and arts and everything like that are part of this woven tapestry, if you will, of space and time and the space-time continuum. So we'll carry on with the next segment here, and that's going to be about what does it mean to do relative age dating. So thanks, and I'll see you in just a few minutes.